Everyone. Welcome to our knowledge sharing session for DOS 4133 operating systems. We are group B12, which consists of Kishan, Faris, Lim San Yu, and I'm Harit, your lecturer for this recording session. Let's proceed with the first subject. All right. Scheduling algorithms, topic one, non-preemptive, my shortest jump first. All right, so we're back here. And as you can see, the P1 has 6 burst time and 1 arrival time. P2 has 2 burst time and 0 arrival time. P3 has 8 burst time and 2 arrival time, with the last process P4 having 3 burst time and 3 arrival time. So here we're going to do the Gantt chart, the calculations. So as you can see, at time 0, there is only P2 because it's got 0 arrival time, so it will move first, and then we execute P2. So from 0 to 2, that's P2. Next one is at time 2, P1 comes in. So 6, which has P1, which has 6 burst time, and P3, which has 8 burst time, are ready. So we basically just put them in, we run them. So we pick P1 first, 2 until 8, and then at time 8, P4 is ready. So we can then proceed to put in P4, which has a burst time of 3. So now it's from 8 to 11. And then finally run P3, which has the longest burst time, so it moves the last. And now from 11, it goes to 19. And that's the Gantt chart complete.
Hi sir, why didn't we run the P4 at the time 3, right? When it was ready with a smaller burst?
Oh, nice question. Because under non-preemptive SJF, shortest job first, a process once initiated cannot be interrupted. So that's why P1 must finish before P4 runs. So now we will calculate the waiting times. Okay, here. So waiting time is starting time minus variable time. So as you can see, P1 um starting time 2. Here you can see it. And then minus 1, which is here, variable time. That's why we get 1. And then P2, 0 minus 0 equals 0. P3, 11 here, minus 2 here. So then you get 9. It's basically the same. It's the formula. So for P4, 8 minus 3, you get 5. And then lastly, to calculate average waiting time, you need to add in, you need to plus all of these processes, 1 plus 0 plus 9 plus 5, and then divide by the amount of processes that is running, which is 4. So then you will get 3.75 ms. That's how you do it. All right. So now we're going to part 2, which is preemptive, shortest job first. And this part, it is now a preemptive. Preemptive, well, the last one we did was a non-preemptive. Um, So we're also going to be using the same table. It's basically just the same like earlier, but this one's a preemptive. Now let's go to the Gantt chart calculations. So P2 will always start first because the arrival time of P2 is 0. So it will run its process first. And P2's burst time is 2. So alongside 2, will any process go in to preempt? No. So it will just run its own process without any disturbance. And then on the next process that will come in is P1, because P1 arrivals time is 1 with the burst time 6. So now we will add in P1 here. But since P1 has 6 burst time, we will see if alongside 6 throughout 6 burst time, if there is any process that will be going in. And yes, at the third burst time, we have P4 going in. So P4 will go in and preempt P1, which had 6 burst time. And now P4 from 3 will go to 6 to finish its own process job lah. It's 3 to 6 and then 3. So now it's 6. P4 has completely finished the job. And now we will continue with P1. Why? Because P1 has a lower burst time than A. It is a preemptive priority shortest job first. So we will run P1 to finish its job until 6, from 6 to 11. And now 6 to 11, we will, no, the last process now is P3 with the burst time 8. So we will just add in P3 from 11 to 19 to finish its job. And now we will go to the calculation, the average waiting time. It's still the same formula, which is waiting time equals to starting time minus arrival time, but it's a bit different because it is a preemptive. How to calculate preemptive's waiting time is P1. So now P1 we look starting time minus arrival time 2 and then 1. We have to do 2 parts. And now 6 minus 3y, because 6 here, because P1 is divided into 2 boxes, 2 columns. And now we take the starting time of P1 here, P1, 6, and then we minus 3. So we will get 4. And then P2, 0 minus 0, because, well, it doesn't have any columns like divided. It only has one program here, process. And then for P3, still the same, one column, one box. So we will take 11 minus 2 arrival time. We will get 9 ms. P4, 3 minus 3. We will get 0 ms. The average waiting time calculation is still the same as well, which is you add in all of the process, you plus them all up, you combine them. 4 plus 4 plus 9 plus 0, and then we divide by the total of processes, which is 4. And then we will get 3.25 milliseconds ms.
Sir,
And that is it. Yes?
does this permission reduce the average waiting time?
Yes, it does, because uh, because essentially the processes cuts up each other, and the average waiting time now is 3.25 ms. It's a reduction from the non-preemptive, which was 3.75. And now we will move on to real life scenarios. Yes?
But doesn't P1 waiting long because for it?
Yes, it does, right. P1 waits longer, but the system performance is better overall. And now we will go to part 3. Wait, before we go to part 3, for example, these are real life scenarios that you can kind of relate to the SJF scheduling method. For the non-preemptive SJF here, as you can see, CPU selects a job with the shortest burst time and does not interrupt once started. As for example, a car wash queue. Even if a motorcycle arrives later, washing continues until the current car is completely done. But for the preemptive SJF, here's an example. Parcel parking. If a smaller package arrives, they pause the current one, finish the small package first, then return to the big one. Because in preemptive SJF, the CPU always runs the job with the shortest remaining time and can interrupt if a quicker job arrives. These are the examples that you can relate to SJF, non-preemptive and preemptive. Going to move to topic 2, deadlock. We're going to be learning about Banker's algorithm. It's a method to check whether or not processes can be run. So Banker's algorithm not safe state. This is the not safe state. So we've got the allocation table and the max table. We've got P0, 0, 1, 0, 2, 2, 0, 3, 0, 0, 2, 1, 2, 1, 1, 0, 2, 2. And for the max, P0, 7, 5, 3, 8, 4, 5, 8, 2, 2, 3, 3, 2, and 8, 5, 3. And for the available boxes, we have 2 for A, 0 for B, and 5 for C. These are given in the question, by the way. All right, so this is the calculation part. This is the answer. So for the need table, you will have to find it out yourself. So to calculate need, we have to minus max minus allocation. So as you can see here, max P0 has 7, but on allocation, P0 has 0, which results in the need table, P0 having 7 for A. And it's basically the same for every box, A, B, C. P0, 4 for B, because on the max table, P0 has 5 on B, minus 1 on B. And 3 for C, minus 0 on allocation, which will result in 4 and 3. That's how you calculate the need table. And now, to check whether or not the processes can be run, we will check whether or not the need is equal or lower than available. So this is the available, right? 205. Let's see. Now P0, 743 on the need table here. We will check if it's lower or equal than 205, which is false because 743, 7 is higher than 2, 4 is higher than 2. But even though 3 is lower than 5, we still have to consider it not possible to be run because the first few numbers are already wrong. And now P1, we checked 625. 625. It's higher than 205, so it's false. P2, 520, higher than 205, false. P2, 121, 205, false. 832 for P4 is higher than 205, false. So for example, if it were to be lower, it would have to be it would have to be said as true. But since it's not lower than the available, it will be categorized as false. So currently the system has available 205. Process P3 requests 121. Although this request although this request does not exceed its maximum need, it cannot be granted because the system does not have enough of resource B. Because the needs for A is 2. The needs for B, of resource B, it needs 2, but available is 0. Therefore, the request is denied. And if the system tried to proceed, it would lead to an unsafe state. It is not possible, and it will ruin the processing. A real-life scenario example for Deadlock, a not safe state. For example, office with one printer and one scanner. Employees hold resources and wait for each other. A system is not in a safe state when there is no guarantee all processes can finish even if resources are available. That's the example, a correlation to Deadlock in not a safe state. That is all from us. Thank you for listening, and we hope that you understand. But it's not finished yet. We have a final Q&A session. So, Kishan, Why does preemptive SJF tend to provide a smaller average waiting time?
Since the shorter process can be interrupt longest ones, um, and finish earliest, shortening waiting time of the short jobs.
Nice one, correct. Good. Is the primary difference of between an unsafe state and a safe state based on Banker's algorithm? Paris?
Yes.
What is the primary difference between an unsafe state and a safe state based on Banker's algorithm?
Mm, there is at least one sequence of the process which will finish without deadlock in a safe state. There is no such sequence as an unsafe state.
Yeah, correct. Nice. Lim, why can't we accommodate P3's request in our situation?
It is because the available resources are not enough. Resources fee is 0, but the request has a need for 2. So to provide it would be dangerous.
Correct. Nice. Excellent answers. And that's the end of our session. Thanks for watching.